Amazing.
Yes, I can see this.
Okay, let's try again. So let me check one slide whether it's no, okay, we can make it, right? Okay, so what is it that we do in sort of traditional complexity? Even in quantum complexity, what we study is sort of classical input, classical output problems, right? The sort of most standard quantum complexity question is local Hamiltonian, where I just give you a description of a local Hamiltonian. I ask you, is the ground state energy above some threshold, below some threshold? The answer is yes or no. And in the middle, then there's some sort of computational model, which could be classical, it could be quantum, it could be interactive, it could be sort of some post-quantum thing. But it's purely a classical input, classical output kind of setup, right? And this has worked very well in the classical world because everything is classical input, classical output. But quantumly, what about the complexity of actually applying Hamiltonian evolution? This is sort of, on the face of it, seems like similarly reasonable as a question to ask in terms of complexity than just deciding this ground state energy question. But it's not quite clear how to even really phrase this in this language, right? We still have some sort of computational model. I give maybe some description of a classical Hamiltonian, but now I also give a quantum system onto which I want to apply the Hamiltonian evolution, right? And then what I want out is, okay, it's in some state, maybe it's entangled. What I want out is the Hamiltonian applied to that quantum system. And it's really just not clear how to even sort of pose the question of the complexity of this kind of operation in this kind of model. And this is not an isolated example, right? So for example, if you do quantum Shannon theory, which some of the people here may, typical protocols are you have an encoder, you have some noisy channel, you have a decoder. And the sort of standard setup that people study this, I sort of give you a description of the noisy channel and I ask you to implement the encoder and the decoder. Again, what's the complexity of that? Seems like a reasonable question. If you actually want to run the thing in practice, you better make sure that you can from a complexity point of view. But again, there's no sort of decision version of this necessarily. And finally, in quantum crypto, which I don't know whether anyone here does quantum crypto, but it'll reappear a lot. There are various sort of fully quantum crypto ideas. One that we'll use as a running example is called quantum commitments, where we have two people, Alice and Bob. And what Alice basically wants to do is she wants to commit to a state, or she wants to commit to a bit quantumly, which you should imagine is taking the bit, locking it in a box, closing the box, and sending the box over, but keeping your key. And then you can open the box later, by sending the key afterwards. And a way she can do this is she can prepare one of two states, psi0 and psi1, depending on which bit she wants to commit to, send over half of that state to Bob as a sort of commitment register. And then later on, she can send over this reveal register here to sort of tell Bob which bit she committed to. And there's this property called computational binding, which says basically, once Alice has locked her box and sent her box to Bob, she shouldn't be able to change what's in the box, right? And more formally, once Alice has sent over this commit register C here, just by acting locally on her side of the system, she shouldn't be able to switch between psi1 and psi0. That would correspond to changing the bit that she committed to. And crypto, crypto is based on computational hardness, right? All of the sort of idea here is this should be difficult to do. But again, there's no connection to traditional complexity because we can't even phrase this question of mapping the states to each other in this decision language framework. Okay, so that's kind of the setup. Now, you might sort of hope, yeah.
All of that is entirely true for crypto in general, right?
It's not entirely true.
What part of what you said is quantum problem? When you talk about crypto, nobody talks about complexity.
People do talk about complexity, right? In particular,
you talk about P-space, P-Pody or something, but cryptography is normally not about traditional complexity classes.
It is to a large extent, or at least there's a very close connection. So especially you can talk about, it is in principle not impossible to try to base crypto on, say, NP hardness. Right? People are trying to do this. This is sort of, there's some like school of like, you base everything on some Kolmogorov problems that are NP hard. It's not practical at the moment, so it's not what people are doing in practice, but it's in principle something people are trying. And you can at least sort of talk about the underlying computational questions in crypto in the language of complexity. So for example, factoring as we all know, is like a classical computational problem that's at the heart of a lot of crypto. And you can ask, what happens if various complexity classes collapse? What can we say about factoring? In principle, we could sort of try to prove factoring is NP complete. That's probably not going to happen, but we could. So there is this connection, right?
Sure, but what you said is not about factoring, it's about the existence of hash functions, something like that. So, and there, nobody talks about complexity theory, even classic.
The existence of hash functions, I mean, do you mean like one-way functions or like hash functions?
Specific one-way functions that
people are again trying to base the existence on, or like trying to connect the existence of one-way functions to complexity things. This is not going great thus far, but at least the language matches, right?
I would argue not. I mean, people tried doing all that stuff, basically didn't work.
Well, but
the 80s, people were like, maybe we can make all of that universal, and they realized that complexity doesn't work. I mean, nobody's basing AES on complexities.
Oh, not AES, no, but like in principle, you can base the, or you can at least try to base the existence of one-way functions on some complexity thing. Again, it's not known how to do it. And in some sense, you can also view just the existence of one-way functions as a complexity statement. You can like, I don't know how familiar you are with crypto, but there's this sort of famous 5 worlds thing, right? Where you're like, one-way functions exist, but nothing else does. What can I do? Just P is now equal to NP. What can I do? Okay, currently nothing. So I guess what I'm trying to say is for classical crypto, our inability to connect it very tightly to complexity is really because proving things about complexity is very hard. It's not because there's a sort of in principle mismatch between what we talk about in crypto and in complexity.
I mean, the existence of a one-way function would imply that computation is possible because classical computation is. So there's the language problem.
Right, so we'll come back to this. Now, many of these quantum things, this is sort of one-way thing where I'm like, oh, this classical assumption exists, implies this quantum thing exists. But for example, in classic crypto, like no one-way functions exist, right? That collapses stuff. Whereas if I talk about, okay, we'll get to this on the next slide, if I talk about quantum bit commitments don't exist as an assumption, that currently doesn't really imply anything. So there's a sort of one-way street to some extent, that's true, but there isn't a sort of equivalence type connection. And I would argue that this is in large part just because the language is completely mismatched.
Just a clarification, because I mean, at the beginning you had the first quantum example that you had was like this evolution or something.
Yeah.
What was it? And you said, okay, like it doesn't match with like it doesn't fit into this model. Can you clarify a little bit? Because I mean, of course, it doesn't have the form of a decision problem the way it's asked, but that's not presumably the point. No, like you could also have classical problems which are not phrased as decision problems. So what is like the inherent, like really like the difference? Like could you have like a problem that is like not fitting into the framework, but is a decision problem on the quantum side, so that it becomes a bit more clear to me, like what is the kind of fundamental?
It is, I mean, this is an excellent segue, so I didn't plan this. You could hope that indeed the complexity of applying these quantum operations in some meaningful sense reduces to decision problems, right? This is what happens a lot in classical complexity. There are like search problems and there's something's a little bit different, but like search problems, for example. Yes, they don't like fit language-wise. If I ask you like search for this, it's different from is the answer to this yes or no, but they are sort of equivalent in the sense if we understand one, we understand the other. So indeed, you could just hope maybe the same happens to unitary complexity, and then then it's really just a sort of translation task if we have to find like the right connection between decision and unitary complexity. So this you could hope for. It's a very reasonable thing to hope for. There's some evidence that this is not true. Most of this is from crypto. So like the QIP before this QIP, Kretschmer, Tian, Signa, and Tal showed that quantum crypto can still exist if P is equal to NP, so in particular this bit commitment primitive can exist. Whereas classically, if P is equal to NP, there's sort of no crypto left, right?
Crypto means bit commitment. I mean, BB84 is not affected by P not equal NP. So
oh yeah, I mean there's no computational crypto left, right?
Okay.
Because you can always like non-deterministically guess the secret key. If P is equal to NP, I'll just guess the secret key correctly and like I'm done. So there's no computational crypto that's left.
Yeah, but I mean BB84 is also survives if P is not equal NP.
Oh yeah, I mean there's also information theoretic crypto primitives. I guess when we talk about this, when people say there's no crypto left, people kind of mean there's no like computational crypto left, which is usually viewed as a sort of more interesting kind from a CS point of view. But yeah, BB84 survives.
What does the statement mean then?
Oh, okay, more specifically, they prove that relative to some oracle, P is equal to NP, but quantum bit commitments exist. And quantum bit commitments can't exist unconditionally because this is all like Meyer's low result.
And what is this oracle like?
Oh, this oracle, okay, it's somewhat complicated. I forget the details. It's some like correlation-based thing. There is an earlier paper just by William, which is a little bit simpler, where he basically like that's about like BQP and QMA, not P and NP, where he basically puts like a random unitary and a P space, sorry, a QMA oracle, I think, and then proves via some sort of power concentration that the random unitary can't help with the QMA, and then it works out. This one is really some like very engineered correlation thing. So yeah, it's not like it's an oracle thing, right? It's not a very natural thing.
Yeah.
And would be good, right? Quantum cryptography would be good.
Second.
Exists in oracle means that it could exist, not that it like they exist currently now in a world where P equal NP could still mean that quantum bit commitment would.
Oh, I mean, so what?
That it always works even in P.
Well, so okay, the way the language works is if I say like there exists an oracle relative to which, it means like if we assume that there's a black box that has these properties, then provably, like I can use this black box in my computation, then provably both P is equal to NP and quantum crypto exist. It's not like there's no contradiction between the two, it's actually relative to this oracle, both statements are true simultaneously.
What it means is that there's no contradiction. It's always those very
No, relative to the oracle, you can prove existence of bit commitments.
yes, but it's always a little tool, not a
So what?
like it's a tool to prove that relative to oracle you have a separation or something, but not.
I'm not sure I get the question.
If P equal NP could be that bit commit is just false. That you can't have one bit.
If P is equal to NP, it could be. So if P is equal to NP, then like there's no oracle relative to which P is equal to NP and classical bit commitments exist. But there is this oracle which they constructed relative to which P is equal to NP, but quantum bit commitments still exist.
That doesn't mean that they still exist. That just means that it's harder to prove that they are.
Yeah, it's oracle based.
Well, I mean, relative to the oracle, they do provably exist.
Yeah, but
I mean, yeah, it's an oracle result. Like it's not a real world result. It's an oracle result. Yeah. Okay, there's a sort of formalization of this idea of, does like complexity of unitaries reduce to traditional complexity? You might have heard of it's sort of now known under this unitary synthesis question banner. Originally just got on Fred Cooper, and the idea there is, can I give you a unitary? Is there some sort of function, like a classical function, that can help you implement this unitary on polynomial time. So in other words, if I give you like all the classical computational power in the world, you can like, solve the halting problem instantly. You can do whatever you want. Does that allow you to implement arbitrary unitaries?
How do you give me the unitary?
Oh, okay. So the formal version is I want you to write down like a circuit, which looks something like. Yeah,
We need to write it, I think.
Well, I mean, okay, the left part of you guys can see really well.
I can see it.
Yeah, we can. You can just move the.
Yeah, I can write this.
That works better.
I guess that's fine, yeah.
Does that work?
I get to ask
Like that's perfect. I think it's harder for you because you work. So it's okay.
That's going to be a very low effort drawing, so too much effort in that. Like the formal statement is like, I want to find an oracle subset, which means I want to write down like the unitary, and then there exists some like OF gate, which is say a phase gate for some Boolean function f. Then I like do another unitary that I write down in terms of gates. These are like efficient quantum circuits.
And this implements the design.
And so on. And then the question is like, for the yes answer to this unitary synthesis question would be, for all unitaries, there exists some choice of function f such that this oracle circuit implements the unitary that somehow.
And it's polynomial depth.
It's polynomial depth, yeah, and each of these unitaries is polynomial complexity too.
Okay, yeah.
It does not make any statement about like finding this function, right? In principle, it's really a question about like, does it reduce to the complexity of implementing the function, but it doesn't talk about the complexity of actually doing the function. So it could be that it exists, but it's like impossible to find.
And so one more clarification, these unitaries that you're implementing, these are unitaries that you are implementing in
Right.
yourself, right?
I'm like a guy and I want to implement a big unitary and I'll do it in a circuit of this form.
I see. Okay.
Okay, now this is it's a question. The implicit conjecture here is that the answer is no. There's a little bit of evidence towards this. Sorry, these are like QIP slides, so it says this QIP, which is that there's a sort of one query lower bound. So this means that if I restrict myself to circuits where I like do something, I do one oracle query, I do something else, that's it, then it's provably not possible. But once you go to two queries, that proof like breaks down completely, and we don't know. So it's a question, but it's generally believed that the answer is no.
Sorry, just the details of this one query lower bound. You apply OF at the location of your choice, and you choose polynomially many gates. Is that?
Yeah, like you do an efficient unitary, you apply OF. I mean, you can like always apply it at the start and just swap stuff, right? You do another unitary, and that's all you get to do. Just as a side note, because I know like probably some of you were like involved with this whole like random circuit complexity stuff. Like your first instinct is to just count and be like, well, there are very many unitaries and there are not as many functions. There's some like R concentration picking up with some epsilon, like doubly exponentially many. That does rule out a circuit where you wouldn't have ancillas. But once I have like 2n qubits, then the counting argument breaks down, right? So the ancilla-free version is easy just by counting, but the version with ancillas is hard.
What takes the oracle twice? Taking the oracle twice would already allow you without
No, it's just like the counting is like there's some number of unitaries. If I like put an epsilon ball on everyone by concentration of measure, it's like doubly exponential. And there's some number of functions. And now I'm just going to be like, well, if my function here, so I suppose I look at n qubit unitaries and n qubit functions, then there are not enough functions to cover the unitaries. But I could use like a 2n bit function to implement an n bit unitary and just use ancillas. And then there's no more counting argument that rules it out. I don't want to like spend too much time on this. It's kind of like
point of this is that like it's just like this unitary synthesis problem is kind of like inherently hard. We cannot reduce it to a classical. That's like the point.
Yeah, the point, like morally, the takeaway here is Thank you. Is implementing unitaries does seem sort of inherently difficult inherently different from just computing functions.
One sort of main question is that, what if the Oracle OF, I just fix it to be the unitary that I wanted to implement and then just measure the first unit as a BQP decision result. So I just
OF is like a phase oracle for a Boolean function. It's a diagonal unitary.
Right, yeah.
So that's kind of the problem. You can also we phrase this in terms of complexity language. You can also just phrase it in terms of sort of compiling question of can I compile any unitary as efficient circuit, inefficient diagonal unitary, efficient circuit, inefficient diagonal unitary, and so on. Okay, so that's kind of the motivation here. We have these fully quantum problems. We want to talk about their complexity because they're important for crypto, they're important for physics. And there's, at the first instance, this language mismatch, but it seems like this language mismatch is more than just a sort of issue of translation, and it's actually a more fundamental mismatch between the concepts. Okay, so this is mostly a slide because, well, A, it's fun to pet tigers, and B, this is to convince you that there are indeed many of these problems, right? So depending on what part of quantum you care about, like in quantum crypto, quantum money, commitments, pseudorandom states, copy protection, one-way state generators, EFI pairs, all of these are phrased in terms of security games that are about mapping states to each other, or at the very least, taking an input state and producing a classical output. But the input in the security game is always quantum. Likewise, I don't know, what people care about the most, maybe this is a physics department. So, preparing ground states, fundamentally a quantum output question, because I want to output the ground state and I want to output some classical property of it. I could talk about verifying ground states as in you give me a description of a Hamiltonian, give me a state, you ask me, is that the ground state? You can talk about decoding Hawking radiation, which we might very briefly at the end. So there are all of these problems. Are there any black hole people?
Yeah, there are black hole people. They are in another building.
And the other building, okay. Well, I'll walk over and say hi. So there are all of these problems, and really the questions that we want to ask is which are efficient, which are essentially equivalent to other problems, like complexity theory, because we can't prove anything unconditionally, is really a theory of equivalences at this point and sort of conjectured inequivalences, right? Can we define sort of some natural complexity classes, have some natural notion of completeness for these classes? And then from a crypto point of view, what hardness assumptions on the complexity side can we make that yield quantum crypto?
When you say efficient here, you mean computational efficiency?
I mean computational efficiency and some notion of computational efficiency that I haven't defined yet. Okay, so that's what we want to do. We want to start from these natural problems. We want to formalize them in some sense, because I can't just show up with a little picture. You need to formalize them, just like we formalize decision languages as these yes and no strings and so on. We need to formalize them. We'll do this as unitary synthesis problems. Then we want to, start proving reductions, classify them into classes, identify complete problems, maybe prove separations and so on. Okay, so I'll give you sort of brief sketch of the current state of this program. Far from complete, but we're getting started. Because let's begin with this question of how to formalize a unitary synthesis problem. So morally, what do we want to do? I want to say, well, here's some sort of quantum input, quantum output problem. What's the complexity of doing this map? And this is very simple to formalize, actually. You just say a unitary synthesis problem is just a sequence of unitaries that are indexed by strings. And we've all sort of implicitly agreed on an encoding from strings to unitaries, just in the same way as in classical complexity. If I give you a string, we've all implicitly agreed that this is say, interpreted as a factoring instance using some sort of encoding. There's some sort of implicitly agreed encoding here, and then the question is, given sort of having fixed a unitary synthesis problem, so having fixed this encoding, I give you a string X, how hard is it to apply the corresponding unitary UX to an arbitrary input quantum system? So I give you the string, I give you some quantum system, you're meant to apply UX, how hard is it? Okay, so let's practice with the definitions.
So isn't now the input again a classical string?
Not in a certain sense, yes, but it's a classical string and a quantum system to which you want to apply. If you want to use this in this like box picture that I had at the start, you now give the string X and you give a quantum system and you get out a quantum system.
Right.
So you could, in principle, wonder like, can I index these unitaries in some quantum way? There doesn't seem to be any good reason to do that. But
And this black box contains both the encoding of the unitary and the application that would at the end give the output of the unitary, the encoded unitary applied onto the input state that you give the black box.
well, yeah, the black box is like trying to do the UX, and we've all like the black box is sort of constructed just like a black box for factoring would be constructed sort of to interpret the string X as a factoring instance. This black box we should imagine as being constructed to interpret the string X as a unitary instance.
Just one very short question, like, because I mean, I guess that's not the point. I mean, the point wouldn't be to be like, oh, it's difficult to find like a way to compile this unitary. Like, or is that the point of this? Like, kind of, you give me a unitary kind of by this label X, and then it's like a hard problem if it's just difficult to like find how to like implement this. Is that the question?
That is essentially the question. Yeah.
Okay.
I mean, that's also the question in classical complexity, right? I give you a big number, and the question is it like difficult to compile a circuit that like finds the factors?
But then it wouldn't make sense to have a polyquantum because it would be like, oh, I give you the unitary. How difficult is it for you to compile it? It's just like, okay, how long is the unitary, right? Like, how complex is it? That's the complexity of that.
Right.
So it's there needs to be somehow like, or I don't know, maybe in my limited creativity, there needs to be somehow like a classical input to quantum that goes to quantum.
I mean, implicitly, like in principle, you could imagine some like quantum encoding that isn't just a unitary, right? Like I could give you, say, like the choice state of the unitary. Be like, well, that uniquely identifies a unitary, please implement it given this state.
But it feels like you're just complicating.
Yeah, it doesn't buy you anything.
Yeah.
That's not the point, is that it should be classical. Like you apply gates or like just a different state, but the point is that it's a classical input to quantum operator.
Like a classical input to a quantum.
Like the task is a classical input, implement that unitary that is described by X, and then the task is implementing that unitary in the system. Right? The input should be classical. Just
it's natural for it to be classical, even for these fully quantum problems, because we're still sort of specifying the problem instance in a classical way. I'm just saying, because people often ask this and sort of want to like answer the question before it's asked. In principle, you could imagine specifying the unitary in a quantum way too. There's no reason to do this at the moment as far as we can tell, but in principle, you could imagine doing it. Okay, let's practice with the definitions. So here's like the dumbest encoding I could pick. Yeah.
Yes, so maybe you will say later, but how does all this relies heavily, this harness on really trying to implement or decompose or compile or whatever this use exactly, right? So if you are allowed to
there's some notion of error.
I see. So you are also allowed to somehow decompose this UX up to some approximation or whatever.
Yeah, well, we'll see this is sort of part of the definition of the complexity class, not the definition of the unitary synthesis problem. So I could define a complexity class as, it's sort of like QMA1, say, right? Is like the exact version. I could also define a complexity class as like BQP exact, which are like all the unitaries I can exactly implement using polynomial length sequences of gates, but then I would have to specify the gate set, and it gets a little ugly.
Exactly, because
whereas typically what we'll do, and we'll see this in a second, it will be something like implement this unitary up to some error that decays inverse polynomially in the length of the string X. And that then just means like, the longer the string, okay, actually we're sort of in the process of changing the definition somewhat, but like, basically, maybe the better, okay, let me give you the new definition, which is I give you the string and I give you an error parameter.
Yes.
Tell you how close do I want the unitary. And then, for example, for like unitary BQP, it would be implemented in like polynomial time of the length of the string X and 1 over the error. So if you want the unitary to within like insane precision, like exponential precision in the length of X, I would get exponential time to do that because I'm polynomial in the error parameter.
Okay, sorry to maybe ask you.
No, go ahead.
How is this? The traditional result, no, by ETH this thing, this mismatch that you have Clifford gates plus three gates, and you can compile any unitary up to this precision with polynomially many gates.
Yes.
So how does that fit into this, or what is how do you see that in this context? Because
that's a good question. Like, how, isn't this all just trivial? Can we just like not?
Or it has to be exact. So that was my first thought. But
it doesn't have to be exact. So first of all, the Kitaev thing is not polynomial time, right? It's polynomial space. So that's the first important difference. It doesn't say that there's a short circuit for every unitary. It just says that there is a circuit for every unitary, but it might be very long.
Right.
So that's the first difference. Now you could still worry. Maybe if I want to define like unitary piece space, where I have polynomial space and as much time as I like, maybe that's just everything. And okay, we'll come to the definitions in a second. The answer there, how familiar are you with like complexity, like non-uniformity and that stuff? Like the answer basically is that like piece space, like the non-uniform version of piece space / poly, would be everything by the Kitaev thing, because the advice basically allows you to just write down the circuit. Whereas the definition of piece space that we'll use is a sort of uniform thing where I give you the string and you have to, in classical polynomial space, write down the quantum polynomial space circuit. And that doesn't that you can't do for the Kitaev thing because there's no efficient way of like getting from the string to them.
Yeah, that makes sense to me.
Yes.
But now that you've touched on it, is this a non-uniform definition?
Well, okay, so there's a distinction to be made here between what is the unitary synthesis problem, like how do we formalize this question of implementing a unitary, which is just this, and how do we talk about its complexity? And the non-uniformity shows up when we talk about the complexity, because then it's like, am I given advice or not? Like alongside the string X, can I request arbitrary advice?
I'm just wondering, let's say the subset was a single, just one element. In the usual uniform complexity sense, it doesn't really make sense because it's a single instance problem then.
Oh no, I mean, you always talk about the sequence UX, right? Oh, okay, when I say here, could use a subset, you have to use an infinite subset. Right? You can't. Are you confused about the
I think he's talking about just additive, but you could have just added just unary encoding of X, and then you only have one element.
Unary encoding.
But if you unarily encode the whole encode node, it's still undecidable, but it's in P/poly. Right.
No, I don't think that's what I'm saying. I'm okay, in traditional complexity theory, I could talk about problems that are single instance problems.
What is a single instance?
Can you give an example?
Where the language is just one string, or just a sequence of strings that for every n maybe there's one string. And usually it doesn't really make sense to talk about these problems because the algorithm is just hard coded to solve that particular instance.
Only if you have /poly.
If there's a language, just as a reminder, in classical complexity, there's yes and no instances, both are strings, right? Now, in principle, I could write down a language where like the only yes instance is like 1, 0, 0, and all the other strings are no instances. That would be indeed trivial, right? Because I would just like, I could decide that language just by like, if my input is 1, 0, 0, output yes, else output no, and like, I'm done. Now, you could have a language where like, for every length string, there's a, like, for every end, there is one end-bit string in the yes instances, and all the other strings are no instances. Now, as I don't know your name, but as you said, like, if you have advice, then this is trivial because for every length, the advice will just tell you, here's a string to check, right? If you don't have advice, it's not trivial.
I see.
Yeah, you don't know. You can't necessarily hard code that for every n.
So
Yeah, I mean, I was serious about. I have no ambition to get through the slides. So
maybe you will get to it. So then just skip it. But because you said for the Kital thing, there is a poly, there's an advice, and I didn't quite understand what. When you were answering.
Yeah. So I'm not sure it's like worth going into this.
Okay.
It's also like
never mind.
And we also
We can also
at the halfway line.
later. Yeah.
The definition then.
like advice in this thing is quite subtle because there's advice that depends on X and there's advice that depends on the quantum input. So yeah, that's maybe like a discussion for another time. Yeah.
So one question, because you're on the definition, and I was still not sure what inherently quantum about this problem. If I take a stab at dequantizing this, let's say that you sort of index the unitaries by a classical bit string X and define the problem such that for all input states, the output state is just epsilon close to the output state that would have been the output of a unitary that I had in mind, and the no instance would be, again, 1 minus epsilon apart from the output state that the unitary would give you. Then you have.
I'm not sure I understood.
So I just was taking a stab at dequantizing the definition of this problem, where you don't take the quantum input as is defined here. We just take classical input, which is the index of the unitary in this class. And the yes instance to this classical problem is then the output that the unitary will give you, output state that the unitary will give you. How close is sort of your output state to the output state that the unitary would have given you?
But how do I like, so there's the unitary.
Yes.
You want to eliminate the quantum input.
Yes.
So now there's like no notion of output state anymore, right? Because if I have no inputs, fixed input state of the unitary, I don't know what the state would be.
I was thinking of indexing a unitary, and for all input states, does there exist a polytime unitary such that the output state would be close to the one that the one of the actual unitary that happened?
Oh, but wouldn't that mean that the identity unitary is already like undecidable because I could have an input state that has the halting problem in it and I do nothing to it, and then it's very hard to make the output state?
Sure, yeah.
I mean, I think
It doesn't seem useful.
The idea that you don't want to dequantize, right? You want to.
I mean,
all the slide, like for all the examples you had, we basically have a precision word. How many of them we have an explicit precision word? Your point is to argue if we don't dequantize and define, maybe we can still get some useful ideas, right?
My point is not so much that I'm like strictly opposed to dequantizing something. Like we're not doing this because we like ran out of classical things to say or something. Like the point really is that it does seem like there is no, for these some of these problems at least, there is no useful classical statement that you can make. Especially like this is sharpest for these crypto problems where because there's this oracle separation, it doesn't seem like there's anything that I could say classically that would impact the existence of, say, bit commitments, like quantum bit commitments.
Yeah.
Okay, let's go a little further with the definitions here. So let's just try them out. So let's say X is a gate-by-gate encoding of a quantum circuit. That's how I want to interpret X, and UX is the unitary implemented by that circuit. Now that's in unitary BQP, right? Whatever that's supposed to mean, because if I give you X, and you're like a time quantum computer in the input length of X, you can very easily implement this. I've already told you which gates apply, just apply them and get done. Okay, so we call this unitary BQP. We can also sort of ask about how can we like embed decision problems into this? Like it should be a sort of superset of decision problems, right? So for example, if X is like an encoding of a BQP decision problem described by some function f of X, which outputs a bit, then I could define my corresponding unitary U of X as, say, like a phase flip. I apply a phase flip of f of X as 1, and I don't apply one if f of X is 0. This is also in unitary BQP, right? Because I get my string X, I solve the decision problem as a decision problem, then I have my bit, and then I apply the corresponding unitary to whatever quantum system I've been given, and that's fine. So you can sort of embed decision problems into this unitary complexity thing.
Is that a defining property of any decision, like that any X class X decision problem should be able to be embedded in a unitary X decision?
I mean, it's not like a formal requirement. It seems like a reasonable thing to want from a good definition. I guess should sort of be able to solve decision problems in unitaries too. So we typically like, when trying to figure out what the correct unitary definition is, yeah, we try to make sure that it's okay. We can play the same one for p-space. Then there's some notion of unitary p-space. Again, I'm skipping over the like uniformity, non-uniformity stuff here because it makes it much more ugly to look at. But you can just imagine this is stuff I can do in quantum polynomial space. Here's the one that we had at the start. I give you some explicit encoding of a local Hamiltonian. The unitary I want you to apply is the time evolution. This again is a unitary BQP by Hamiltonian simulation. Right? There's some algorithm that does this to like very good precision given the description of Hamiltonian. Yeah.
Do you have a difference between unitary BQP space and unitary P space?
No. Yeah, this is a bit unfortunate. Like, so BQP space as a decision problem, as a decision class is equal to P space, right? This is like what we're saying.
Might not, like, I mean, depending on where you, maybe.
Well, there's sort of like unitary P space as a classical thing doesn't make a ton of sense because like there is no sort of two versions of unitary P space. There's only like the fully quantum version. So arguably we should call it unitary BQP space, but everyone, like no one ever talks about BQP space, so we call it unitary P space. Okay, so I appreciate all the questions. It does mean that we're really slow. As I'm reminded, we have like a talk slide thingy that says this should be 19 minutes in and 43 minutes in. So we'll maybe skip over this part. And that's not working again.
Yeah, I feel like if we get like the basics, I think that's.
Yeah, so there's an important average case notion, but let's skip over this and go to reductions, which is really the sort of heart of complexity theory. And this is also like thus far, especially if I had told you the sort of full uniform definitions, this still sounds pretty classical because it's about like, oh, I want to like, uniformly print out a quantum circuit that implements this. So then it still sounds like, okay, the input is like a string X and the output is like a quantum circuit description. But the reductions is really where it becomes fully quantum and stops looking classical in any way. Okay, so what do we want to do in a reduction? We want to say like Ux reduces to Vx, so both of these are unitary synthesis problems. And morally, what we want this to mean is, if I could solve Vx efficiently, like if I had a magic box that solved Vx, then I could also solve Ux. The way to formalize this is sort of similar to this, which is with these oracle circuits. So an oracle circuit is just so suppose I want to have an oracle circuit for Ux that uses Vx, gates, oracle gates. This means I write down a circuit. And, I have the normal sort of gates and I just specify them. I'm put a C0 gate here, I put a Pauli Z gate here. And then I have these special V gates. And these are just specified by the index like Y. And, the Y doesn't have to be the same as the X. I can use like different sized instances. And And we say that UX reduces to VX if there is an efficient oracle circuit for UX of this form that has a normal gates and then these V gates that we count as like one time step in the circuit.
Just to check, the y and y prime here have to be classically efficiently computable from X.
That's a good question. You could go with either. Like in the definitions that we use, the answer is yes, because you want, like, this is sort of, again, this uniformity thing where I give you the X and you want to like efficiently write down the circuit. Right, so writing down the circuit includes writing down the Y. Yeah.
Can they be specified by the rest of the circuit?
Again, you could use that definition. Currently, we don't because we don't see any reason to. But yeah, you could in principle have some sort of like dynamic, like computate, like dynamic. I could like put a gate here that is just of some fixed size and has an input for the string Y that has been computed before and a quantum input. You could do it as no reason.
So the idea that the Kluber is a quantum machine. Efficiently computable, the Y and Y prime would be BQP, like on a quantum computer. Efficiently computable or a class like. I think the only real difference, I think, between whether you can use them as feed forward or not. If you are a classical computer, you can't solve BQP problem.
Oh yeah, for BQP this is not so interesting, but you can have certain like fancy interactive classes and so on. And then you want that the Y say is like as the classes become more and more complicated, the uniformity thing becomes more and more subtle, because then it's like, what does the classical thing do that like prints out the quantum thing? And then yeah, there can be a sort of mismatch. But indeed, if you, as you said, if you have a BQP machine printing out a BQP circuit for another BQP machine, then it's equivalent whether you have this on the fly computation. Okay, now I want to move on to what is sort of the central point of all of this. Like, the point is not to just have the theory, the point is to say something interesting. And what we want to say something interesting about is basically the complexity of applying the Unitarian Uhlmann's theorem. And you might think this is a sort of somewhat like quixotic enterprise, like Uhlmann's theorem is a good theorem, but like, you know, why apply this one? The reason is that, as you know, I would tell you if we were a bit faster, there's like many applications that essentially reduce to this Uhlmann transformation problem that I'm about to define. So we'll hopefully, you know, get to that, but here's a very brief list of, you know, where do these Uhlmann transformations show up? So if you do quantum Shannon theory and you know these like decoupling style things, the decoder in a protocol is basically just implementing an Uhlmann transformation. Quantum state compression is basically implementing an Uhlmann transformation, as is entanglement distillation. If I have any quantum interactive protocol, like a QIP protocol, the provers I can always view as just implementing Uhlmann transformations. So I purify the protocol. Breaking binding and quantum commitments is implementing an Uhlmann transformation. Breaking these unclonable state generators is. Even decoding Hawking radiation is really just an Uhlmann transformation. So really everything is an Uhlmann transformation, is the point. And if we understand the complexity of this Uhlmann transformation, then that allows us to immediately say things about the complexity of these other problems, because we now have a useful notion of reduction, right? We can say this reduces to the Uhlmann transformation problem, and therefore blah, blah, blah. Okay, now what is this Uhlmann transformation problem? Well, yes, everyone has seen Uhlmann's theorem, but just in case, what Uhlmann's theorem says is, I give you, okay, it makes a statement about fidelity, which is that if I have two reduced states, let's call them psi and phi on some registers B, then the fidelity I can write as I take any two purifications of these and I look at the sort of maximum overlap if I only act on the purifying system. Okay, that's Uhlmann's theorem. What we call an Uhlmann transformation is if I give you two bipartite states, psi and phi, and I tell you where the bipartition is, we call the Uhlmann transformation between these two states that unitary that achieves this maximum here. So it's a unitary that only acts on one of the two parts of the state that achieves the maximum overlap.
So you start from the purification.
Yes, the Uhlmann transformation is defined with respect to fixed purification. Okay, now there's one subtlety here, which is that this is not unique. Let's just ignore that. Okay, so here now is the Uhlmann transformation problem, which is a unitary synthesis problem. So we have a sequence of unitaries indexed by strings, and I need to tell you, if I give you a string X, what should you interpret this as, and what is the corresponding unitary? So what I want you to interpret the string X as is a circuit description of two bipartite states. Let's call them C and D. And the circuit description here, it also includes, like, it also tells you like where the bipartition is, like what part is A, what part is B. And then the corresponding UX is the Uhlmann transformation on system A for this pair of states. Yes.
When I think about the states that you use here as input, should I kind of think as the interesting states being states that have efficient quantum circuits? Because I guess you want to scale polynomially in the length of X or something.
Right. The complexity will scale polynomial in the length of X. So it is well defined to talk about the Uhlmann transformation problem between extremely complex states.
Right.
But it's kind of not that interesting because then I have like a lot of time to.
I guess you could in principle pick like that. So this would change the problem, but you could change it. You could use a different mapping from X to states and therefore U of X.
You could use a different encoding. The good thing about this encoding is that it is closely related to all of these.
Yeah, it makes a lot of sense.
Problems. Sort of, what is this meant to capture? Like, why do we give a circuit description, then talk about the complexity and the length of the circuit description? Is because sort of the question of, well, I have two states that are like reasonably easy to prepare if I have access to the full state, right? If the unitary, this Uhlmann thing, like wasn't restricted to some sub region of qubits, but it could act on everything, it'd be very easy to do this. I would just undo the D1, say, and then do the C1, and I'd be done. I would have mapped them to each other. So it's really a question about, okay, if some of you aren't this like black hole stuff, they talk about like the restricted complexity versus the unrestricted complexity, which is like the unrestricted complexity is the complexity if I can do anything on any qubit. The restricted complexity is I can only act on some subsets of the qubits. And then really the interesting thing is, what's the relation between this unrestricted complexity and restricted complexity? And this is sort of what this is asking, right? The unrestricted complexity would just be the length of this input string X, and the restricted complexity would be how complicated is the Uhlmann transformation. Of course, so then the other part that I can't access, it's like in some black hole or some other universe or like in a wormhole. Yeah.
One more question, because I don't know enough about Uhlmann. If I know that C and D are efficiently preparable, do I know that the corresponding Uhlmann transformation is that is an efficiently implementable?
It's precisely not. That's kind of the good, that's what makes it interesting, right? This restricted complexity, the Uhlmann complexity can in principle be much, much higher than the unrestricted one. Okay, let me tell you a couple things about the complexity of this sort of in general, and then maybe run through like one example where it shows up, and then we can like continue chatting over lunch or afterwards. But
I'm still confused, to be honest.
Okay.
I would like to understand maybe okay, I can think of this in this what do you call it, uniform complexity classes, and you will like put it in some complexity class. But why? I think I can still think about this in like traditional complexity terms. No, like where am I stopped to say, okay, you give me this unitary, you give me this description. I know it corresponds to some. You give me this description of the states. I know the problem. It's to find this unitary. If I can say, okay, like I don't know, you can find. Let's say you could find this. Solve the problem of finding a description of the unitary in polytime, and I then have a circuit which takes how many gate elements to implement that unitary. Okay, that's then the complexity.
Yeah, that's precisely why I asked my question.
Sense.
I think that has to do with my question. Like, if it were true that these Uhlmann transformations for efficient states are always in principle efficient, you could phrase the classical question.
But even if it's okay, like let's say the classical problem of finding that unitary is itself exponential, whatever, I put it in some complexity class. And then the circuit complexity of that unitary is also something, then that gives me the combined complexity in the traditional sense, I would say.
Then it means that it's strictly an exponential time algorithm.
Sure.
Which is not the same as saying that you define some in between exponential time quantum unitary and polynomial time quantum unitary, right? Like the point of these complexity class will always be to have something that's not efficient or practical, but that's not as complicated as the arbitrary most complicated class, right? That's
So
the point of NP and anything else.
Is that kind of the point that like I could try to phrase it like that, and then you're giving like a more fine-grained.
I think so. Let me try to rephrase the question in like how I would maybe phrase it, and you tell me whether that's correct. You're basically saying, well, like if I do this uniform thing, what do I get as input? Really, I get as input a classical string, and I'm gonna like have some classical, let's say unitary BQP, I have some classical Turing machine. It prints out a classical description of a quantum circuit. And now I make this sort of extra move of saying, well, instead of just talking about that part, I also then consider the quantum input and applying the quantum circuit and getting an output state. Why don't I just stop sort of one step early and say my input was the string, my output is a quantum circuit to do the unitary classical input, classical output, I'm done, right? Is that sort of what you're asking?
I mean, that's anyway.
Right.
I think that's the main question that I had with this paper. Like, I can justify, right? You need to justify.
I'll answer that question in a second, but maybe let's just like check what the question.
Maybe it's like maybe like it's a fine misunderstanding of the quantum, like BQP, let's say, or classes of that form. But like there, isn't it like okay, I have a classical description and I want to implement that unitary. How many? Or like no. Like couldn't I talk about like the circuit complexity of implementing that unitary that you printed out in classical in this first step? You did that first step. You have now your classical description of the unitary, and now I still need to implement it, right? I mean, to get the output that you want. Isn't that the?
And I think that's a problem that you would consider one of these quantum problems, right? Given the circuit description of the unitary, implement the unitary.
Yeah, that's okay. Yeah, I see. Then I think I understand that the kind of like that extra step is the difference.
Now, there's still a question of why do the extra step, right? You could just stop short and just talk about, like even for like quantum interactive protocols or something, you could just talk about as a verifier. I described the verifier. Like classically in terms of quantum circuits, like what does it do in each step? I give you the sort of source code. Why don't I just take that as the output? And the answer there is really like in the reductions. Like that's where like the definition itself, you could make that way, but then reductions would start looking extremely weird. Because if I want to say like, I can like, if I want to say UX reduces to VX, what I mean is if I have what I want this to mean is if I have a black box that does the unitary VX, then I can write down a circuit that uses this black box inside that does a different unitary UX. Now that sort of outer unitary, the oracle circuit, I can again write down in a classical way. But if we didn't do the extra step and we just took a classical input and a classical output, then what would a reduction look like? It would now say, well, I have a unitary VX and I have this thing that is a decision problem, right? So it would be something like, is the 12th gate of the circuit implementing this is C0 between these two qubits? And then a reduction would be, I get to like access this classical thing to like make a new circuit for myself for the problem UX. And that'd be a very different notion of reduction. I wouldn't capture this idea if I have a black box that does one unitary and I want to use it to do a different unitary. That would sort of capture the idea of I have like, Oracle access essentially to a compiled circuit for one problem, and I want to use it to talk about how hard is it to like compile a circuit for a different problem. But it, for example, wouldn't allow me to do like apply the unitary BX in one time step. It would just like tell me in one time step what one gate from that unitary is. So really like the reductions is where it stops. Like before that, I agree, it makes sort of as much sense to just talk about classical input and the output is a classical description of a circuit. The moment you go to the reductions is where you sort of run into this necessity of actually talking about the quantum problem as this black box.
Can I maybe paraphrase if I understand this correctly? So for example, you have a reduction, you want to reduce a very powerful thing which can implement unitaries that, let's say, have exponential depth or something like this, if you compile them a reasonable gate. Then if you would just like take the printout of the circuit of this, you cannot just like put it into a new circuit and say, well, I have a polytime thing now that uses this, because like the thing, if you just like use the printout and put all the gates, it will take exponential time. Is this like part of the matter?
So maybe like this is really like a very important point I want to like emphasize. Suppose we want to like define, unitary X completeness. Let's say like unitary P-space completeness. I want to say this problem is unitary P-space complete. What do I want this to mean? I want this to mean if I have a black box that implements this problem, then in polynomial time, I can reduce any other problem in unitary P-space to that one. So in other words, that black box enables me to implement any other problem. If I use the definition of the classical output, that wouldn't make sense, right? Because now just implementing like one query to the unitary P-space unitary, I couldn't do efficiently, right? I would only get like Oracle access to the gates, and that wouldn't make sense. So yeah, the reductions is really like the moment where, as you said, like it sort of becomes necessary to talk about this as one black box unitary that we do in one time step.
And for the reductions, you need to have, it has to be, you have to have quantum access to this Oracle unitary that you're assuming at the back end, and that's what makes the quantumness in the proof necessary.
Yeah.
Just one final question from my side. Would it make sense to like just not have the X here and have the input just be the quantum states?
Right, that's another good question. You could say, well, if I have these two inputs, why don't I make like the X sort of part of the quantum state? Yeah. Like, why don't just like, I mean, I could formally always do this, right? Just put like a cat around the X and put a tensor product and then like, boom, it's one quantum state. You could do this. The reason we don't is because we don't, if you did that, the natural thing would be to allow for like superposition queries. Like then, you would, it's sort of the difference between like talking about like, this unitary, where if now I have like a superposition of different X's, I want to do this unitary, versus talking about just this unitary.
I mean, you could still measure getting it.
You can, but it's sort of like a bit weird to make the input quantum and then be like, oh, but no super, like, be a little hard.
I interpreted your argument like, I mean, it's still basically classic in some sense what you're talking about. Like inputs are classical, what you want to compute is classical, you want a quantum circuit. You basically use pointers to the solution of your problem in the circuit description, in your reduction. Like stuff should be still basically classical, right? You shouldn't be above sampling complexity or anything. It should still be above. It's kind of a circuit compilation question with pointers to solutions to subroutines.
You can view it as that, yeah.
Not as a full quantum input or output complexity. Yeah.
Well, I mean, that's sort of a like question of language. Like the problem instance is still specified classically. Like which unitary I'm talking about is specified classically. Okay, now let me actually like just run through some sort of results and examples quickly, and then we'll wrap up. So, okay, what can we actually say about this? Firstly, you asked maybe, is it easy? There's actually a somewhat easy example to see that it's not, based on one-way functions. I'll skip it for the reason of like the time. So okay, let's say Uhlmann is not at least trivially easy. If one-way functions exist, you can look at this example and you see it's not. Maybe we can reduce it to traditional complexity. Again, we can't. Like, there's no traditional complexity assumption that allows us to say Uhlmann transformations are easy, even if you like gave me the ability to solve the halting problem in one time step, wouldn't tell me how to do an Uhlmann transformation. So what can we say? Well, we can say that it is complete for this great complexity class called unitary average unitary SEK, which is the sort of unitary version of statistical zero knowledge. If you don't know what statistical zero knowledge is, don't worry, it's some sort of interactive proof system. So there's some sort of average case version of this, and then there's some unitary version of statistical zero knowledge, and this turns out to be complete.
Sorry, just because you skipped over this before as well. When you say average case here, is that average case over the classical descriptions of these unitaries, or average over the quantum states that I feed into the unitaries?
It is, the short answer is imagine it's average case over the quantum states. Yeah, it's essentially like there's a distribution of quantum states from which I sample. And there's also like a version of succinct Uhlmann, called succinct Uhlmann, where instead of giving you like explicit, like gate by gate descriptions of the quantum states between which I want to do the Uhlmann transformation, and give like a succinct description of them. This now gets sort of into this sort of more Baroque like complexity theory thing, when I have like a Turing machine specifying a circuit for a state. Then I feed the description of that Turing machine to another Turing machine, and that Turing machine is meant to like output a quantum circuit that does it, etc. It's a reasonably defined thing, where these are described succinctly, and we can prove that this is complete for average unitary P space, and also that it's complete for average unitary QIP, which is a sort of interactive model of applying the unitary. And then the two are actually equal. So this is like there's a P space equals QIP theorem from like Watrous et al. From a while ago, like maybe 2 years ago, Henry and I proved like a state complexity version of this, which is like state QIP equals the state P space, and now we have this unitary version.
So the distinction between Uhlmann and succinct Uhlmann is only the way X is mapped to UX? Yeah.
I mean, every unitary synthesis problem in some sense is about that mapping, right? So it's basically just how do I interpret the string. Okay, so these are at the moment kind of the purely complexity theoretic statements we can make. Now let me just like go through one quick applications and skip over questions for the time being, unless it's like a very urgent one.
My question would just be, Uhlmann is not unique. So how does anything of what you're talking about?
Okay, you can define a unique partial isometry for Uhlmann, and then basically the thing like the what it means to implement like everything, like we call it unitary complexity. Really, it should be called like partial isometry complexity. Every time I said unitary, really it's a partial isometry, and then we talk about any unitary extension of the partial isometry. So you implement the partial isometry correctly if you implement any unitary extension of it.
Okay. So all acceptable. All solutions are
any extension is a valid solution of the partial isometry, and the partial isometry is really the sort of fundamental thing that we want to implement.
Exactly the isometry, not approximately the fidelity. Like you need to have an isometry that like epsilon close to an isometry that exactly implements the fidelity, not being somehow epsilon close.
Again?
You need a unitary that
same, no?
What?
It's not the same.
I think this is just José's question from before about whether you care about exactly achieving something or approximately achieving something.
Is it the same?
You are asking about like where you put the epsilon. If say, can I find a unitary that gives me the fidelity minus epsilon, or get an epsilon close thing that to the thing that gives me the actual fidelity?
I don't think those two are the same.
Okay, like the geometric picture is you have the partial isometry, which is an exact thing. It's like one partial isometry, it's uniquely defined. Then you have a sort of set of unitaries that are all the unitary extensions of this partial isometry. That is still like exact unitary extensions of the partial isometry. And now I take that set of unitary extensions and I sort of thicken every unitary by a little epsilon ball. And I say, now the union of all these epsilon balls of all the unitary extensions, that's sort of the set of like unitaries that I would consider like a valid solution. You got to implement one of them.
That's not the same as the set of unitaries where your epsilon close to the optimum fidelity. Those two are different.
Oh, I mean, there's some sort of continuity there. Like the partial isometry basically says like between C and D. The reason it's a partial isometry is because the reduced states could have like limited support. So whatever you do after the support, like on the orthogonal, like the partial isometry has a kernel, right? Whatever you do on the kernel doesn't matter for the fidelity.
Yes,
so then the epsilon sort of, it doesn't matter whether you put the epsilon there or there.
But if you have an approximate kernel, the isometry would still be exactly defined, but the fidelity would not be affected.
Yeah, maybe we can like do this after. It's not a very central thing. Okay, I can give you like one final example just to see how this now like shows up in these bit commitment things, and then we'll stop. Okay, so we already saw this as Alice as Bob. Alice wants to commit to a bit B. What does this mean? She prepares one of these two states. She sends a commit register to Bob. And now there are two properties. One is called statistical hiding, which means Bob shouldn't be able to find out what Alice's committed bit is just from his commitment register. So formally, this means this is not a computational thing, it's a statistical thing. So these are like close and trace distance. Then there's a reveal phase where Alice now wants to tell Bob, what was my bit? So she will send over this register R, and now Bob has the full state, and the two are orthogonal as complete, like as full states of both registers, and he just measures and knows. And the computational binding property says, Alice, just by acting on register R, can't switch. Okay, how is this in Uhlmann? Well, firstly, this result you probably all know. Is it like possible for unbounded Alice to switch between psi0 and psi1? So in other words, is a computational assumption necessary? The answer is yes. Here's a proof. Like this is from '96. So you can still like write papers about this complexity of proof. You have these two commit registers. They're like close, right, in fidelity, because that's the statistical hiding property. It says these two to Bob look identical, so the fidelity is basically 1. But now by Uhlmann's theorem, the fidelity being 1 means that if Alice only acts with a unitary on her side, the optimal unitary must map these two identical to each other, which means this Uhlmann unitary is precisely the unitary that would break the commitment. Okay, now you can see how this is going to get related to Uhlmann, right? Implementing the Uhlmann transformation between the two states, psi0 and psi1, on the reveal register, the one that Alice keeps to herself. This is precisely the same as breaking the computational binding property of the commitment. Okay, and now the sort of nice thing that this unitary complexity stuff allows us to do is to actually give, and this is rare even in classical complexity, is to actually give the precise complexity theoretic sort of characterization of the existence of this thing. So we know that, if Uhlmann were an average unitary BQP, that would imply commitments do not exist by this proof, right? That unitary exists and it's basically just an Uhlmann unitary. So if it were a unitary BQP, then I could always break it. Now, conversely, if it's not a unitary BQP, then we can prove that this sort of hard instance of the Uhlmann transformation problem gets you a weak quantum commitment. And then you can sort of amplify this to a strong quantum commitment. So really what we get is Uhlmann being an average unitary BQP is equivalent to the existence or non-existence of commitments. This is now a two-way implication, not just a one-way function exists implies thing. And we also know that this is complete the average unitary SEK, right? So this tells us that the existence of quantum commitments is equivalent to this purely complexity theoretic statement that average unitary SEK is not equal to average unitary BQP. Okay, so this kind of reestablishes a very tight connection between crypto and complexity. Yeah, there's like a lot of time, right? Okay, I could give more examples, but maybe let me stop here. And I'm still around for the rest of the afternoon, so I'm happy to chat if people have more questions. But yeah, thanks for all the participation. That was very fun.